Today I'm going to explain the 6M project which is going on progress from the last semester, water quality monitoring system and project members as shown in this slide, and the supervisor is Professor Dr. Ramkaji Purathoki, and this is the outline of this project. Um, we will go through all these topics. Introduction. It is basically the water quality monitoring system, which has the sensor integration of pH, turbidity, electrical conductivity (EC), total dissolved solids (TDS), and temperature sensor. Traditionally, laboratory testing and other monitoring system is time consuming, which is not suitable for real time monitoring. So, to detect the contamination and degradation of the water quality, which is a very crucial part of our life, we decided to go through this project that will measure the water quality in a real time, and we came up with these five sensors. I already told that there is a problem of conventional methods which rely on periodic sampling and lab analysis, which will cause the delayed detection of contamination and lack of real-time feedback. So, mm, we go for the temperature variations, dependent temperature dependent variations like pH, EC, and TDS measurements. Um, we go through the designing of an automated system capable of continuous real-time monitoring. So we will integrate multiple sensors simultaneously for achieving reliable and stable data acquisition. Okay, the main objective is to design and implement water quality monitoring system for real-time measurement of turbidity, pH, EC, TDS, and temperature, and to integrate suitable sensors with a microcontroller and apply calibration and temperature compensation for accurate data measurement. To provide continuous and reliable monitoring of water quality parameters to reduce dependence on manual testing. We go through these papers, and we do the literature review of these, and we finally came up with the idea to integrate five sensors: turbidity sensor, LGZT, which measures the water quality by detecting light scattering caused by the suspended particles, and pH sensor, which has the glass electrode with module, which measures the acidicity or alkalinity of the water, and TDS sensor module, which measures the total dissolved solid, along with the electrical conductivity. It will measure electrical conductivity first, and then the multiplication by some factor will give the TDS value, and temperature sensor we have chosen DS18B20 temperature sensor, and we all these sensor data is fed into the Arduino microcontroller, which collects, processes, and converts the sensor signals into readable water quality data. And then we go for the LCD display for the better visualization, and later on we will go for the detection of water quality in a warning or safe zone by LED indication. Okay, let's move on to the sensors details how the sensor works. LGD sensor is a turbidity sensor which measures the cloudiness and dottiness in the water. There is a two end in the sensor. One end has the LED IR LED, and another end has a photodiode or phototransistor. When the light comes up from one end, it will receive by the photodiode or transistor. If there is a dirty water in between it, then there will be light scattering and absorption of the light, which will cause the less light to be reached in the uh, mm, another side, that is photodiode or phototransistor, which will cause the less voltage of the sensor. Means there, if there is a high turbid water, then there will be less voltage, and if there is a clean water, then there is no scattering and no absorption of light, so all light can go to the photodiode transistor, and which will cause the more voltage output of the sensor. So clean water means high voltage, and dirty water means low voltage. Now we can see there is a graph which shows low voltage for the low voltage for the high turbid water, that is the working. High turbid means low voltage, and less turbid means high voltage. We can see from the graph. Here is the graph, and there is a supply voltage of 5 voltage, a DC. Operating temperature is 0 degree Celsius to 50 degree Celsius, and output is analog, and voltage range from 0.5 volt to 4.5 volt, and measurement range is 0 to 1000 NTU. TDS meter, because of the line there is a problem, so let's move on to the TDS meter version 1.0 EC based specifications. The working of the TDS meter includes two electrode. In between there is a wire. If there is a high conductivity, that is more ionic solids in the water, then there will be high conductivity. And if there is a high conductivity, then there will be more flow of current, and more flow of current is corresponds to the more voltage by the signal conditioning side. So for the high voltage, there is a high electrical conductivity, which is related to the TDS, total dissolved solids. So high voltage means high TDS value, and low voltage means a low TDS value, which is shown in the graph. And the operating conditions are supply voltage 3.3 volt to 5 volt, operating temperature 0 degree Celsius to 50 degree Celsius, and output specifications analog voltage, and range is from 0 to 2.5 volt. TDS range is 0 to 2000 ppm. Okay, let's move on to the pH sensor specifications. pH sensor, how the sensors work. In pH sensor, there is a glass electrode and the reference electrode. Glass electrode, reference electrode, there is a fixed potential, and the glass potential, there is a S plus ion concentration which decides the voltage there, and the difference of these two electrode is the output voltage of our sensor. Let's assume to analyze this concept, to calculate the pH, let's assume the reference voltage to be 100 millivolt, and glass electrode voltage range from okay, let's say for the high H plus ion concentration, there is a voltage of 100 volt. There is a voltage of 50 voltage. Then 50 minus 100 minus 50, it means 50. There is a high voltage for the high H plus ion concentration, and if there is a less H plus ion concentration, let's assume it to be 0. Okay, 5 volt. So 100 minus 5 is 95 volt. 100 minus 5 is 95 volt, and 100 minus 50 is 50 volt. So for if there is a okay, for high, the difference is the output, and if there is a high pH, IH plus ion concentration, that is 50 volt, and the reference voltage is 100 volt. So 50 minus 100 is minus 50 volt, which is greater than 0 minus 100. 5 minus 100 is minus 95 volt, which is greater than minus which is lesser than minus 50 volt. So minus 95 is lesser. So for less H plus ion concentration, it shows the difference shows the less voltage. So less voltage means high pH. Less voltage means high pH, which is shown in the graph. We can see that for less voltage, there is a high pH. Okay, that is for 5 volt. There is a difference of minus 95 volt difference, that is less voltage. For a less voltage output, there is a high PS, because low H plus ion concentration means high PS. So in this way, this sensor works. Operating conditions: supply voltage is 5 volt, operating temperature 0 degrees Celsius to 60 degrees Celsius, and output specifications: output type analog type, and voltage ranges from 0 to 3 volt, and PS range is 0 to 14. DS18B20 temperature sensor. All other three sensors works. Their output type is analog type, but this is the digital type that output. This temperature sensor has the electrical resistance or voltage sense wherever there is a temperature change, and according to that changes in the resistance, that analog changes is correspond it changes to the analog parameter changes to the digital by the ADC inside the temperature sensor, and that digital data is sent to the Arduino microcontroller, and then it will again transform the digital data into analog to give the temperature value. This DS182B20 sensor works on a digital one wire protocol. That is, it cannot make the output itself high. Also, we keep pull-up register through 4.7 kilo ohm the PCC to the output signal, and the output is connected to some Arduino microcontroller output signal output pin. And whenever there is a low voltage, then it will keep low, and whenever there is no low voltage, it will default there will be high. So in this way, one wire protocol is used, and there is a supply voltage of 3.0 to 5.5 volt, operating temperature of minus 55 degrees Celsius to 125 degrees Celsius, and resolution is 9 bit to 12 bit, and we have used 11 bit resolution. And for 11-bit resolution, the formula for resolution is 1 by 2, 2 to the power n minus 1, 8. So calculating it for 11-bit, there is a 0.125 degrees Celsius accuracy. Resolution and accuracy is plus minus 0.5 degrees Celsius within minus 10 degrees Celsius to plus 85 degrees Celsius. And we can see for the digital output, there is a temperature variation. This is the characteristic curve. And based on what I have discussed till now, there is a LGD sensor for the suspended particles in the water, which sensor keeps the analog output, and the range is 0 to 1000 NTU, and the nature of the curve is nonlinear. Similarly, TDS measures dissolved solids analog data output 0 to 2000 parts per million, and nonlinear graph. pH sensor all acidity and alkalinity measurement analog output, and 0 to 14 pH, and linear negative slope linear graph. And DS18B20 temperature sensor digital output, and minus 55 degrees Celsius to 125 degrees Celsius measurement range, and linear positive linear graph. Okay, literature review and parameter selection we have done, and the sensor selection based on availability and accuracy we have done. Individual sensor testing is done. Calibration using standards references we have done it, and microcontroller interfacing data processing we have integrated the sensor system in, and we validate the output by the calibration. This is the block diagram: water sources and sensors, turbidity sensor, pH sensor, TDS sensor, and temperature sensor will. Okay, one thing about the pH sensor remaining, that pH sensor output is ranges from minus 140 millivolt to 140 millivolt. So to operate it in the range of 0 to 3 volt, we use a single conditioning. So pH sensor with single conditioning, and all other sensor, and all the data is sent to the microcontroller, and furthermore, it is displayed in the display unit. This is the overall simulation of our project: turbidity sensor, TDS sensor, pH sensor, and we have used the pull-up register for this temperature sensor, and we have connected the LCD with I2C module, and this is the indication of the red is indication of the safe water remaining under these parameters, and yellow for warning, and green for red for warning, yellow for red for very hazard water, and yellow for warning, and green for safe water. This is the simulation part. And WQI calculation, parameter WHO standard, turbidity 1 to 5 NTU, pH this range, electrical conductivity this range, temperature this range, and TDS this range for the safe drinking water. And this is the calculation of the WQI, which is the water quality index, and this will measure the quality of the water by the um, we have given the turbidity, pH, EC, temperature, TDS value, and this is 0 to 100 value range gives a safe water quality, and 100 to 200 WQI will give the warning, and 200 greater it will give the high risk. And this is the calculation formula, unit weight formula, quality rating formula, and WQI formula. By with the help of this, we can calculate the WQI for the water. Calibration, we have done the calibration of all other sensor. DS1 AB20 temperature sensor calibrated using lab thermometer, turbidity sensor calibrated using turbidity meter, pH sensor calibrated using standard buffer solution of non-pH 479, and TDS sensor also calibrated. This is the calibration table, and we have used this equation to keep to reduce the error in this range before there is a error of 1.60% and after 1.13%. This is the calibration curve. True temperature and temperature. This is true measure temperature, and this is true temperature. We can see we calibrate to validate the data. Similarly for pH sensor, this is the equation. This is the measurement, and non-pH sensor measure pH, and after calibrated we reduce the error. Likewise, we have done for calibration for pH sensor, turbidity sensor, TDS sensor. All the sensor is calibrated, and we have integrated all the sensors in breadboard, and there is dirty water and clean water. We have measured the parameters, and it is shown in the LCD display. You can see there is a TDS, EC, pH, and turbidity for 0.3 NTU, pH was 7.64, EC 116 micro 7 per centimeter, 58 ppm. This is for the drinking water, and this is for the dirty water. 7.06 pH to 93.1 NTU dirty, and that is EC 822 micro 7 per meter, 411 ppm. This is the node rate for the display. In the node rate, we have this in the node rate display dashboard, and this is the display in the node rate. We can see there is a temperature, pH, turbidity, TDS, and EC measurement live parameters, and it will keep the overall water quality after calculating the WQI. There is a warning, there is a safe, and we will proceed our project like this. And okay, August, mid of the August, this project will be finished. We have accomplished the works, parameters finalized, sensors selected, sensor testing of sensors, sensor calibration completed, dashboards designed, simulation of all sensor performed, hardware built on breadboard, testing of hardware sensors for drinking and dirty water, displayed output on LCD display. This is the work accomplished till now, and future work includes make a device portable, organized, and ready for real-world use. Build a need to part enclosure toward the entire project, sampling chamber where the water and sensors goes, keeping the wet parts contained. A second box will safely hide the electronics, microcontroller, and power supply, completely protecting them from any accidental water damage. Add a simple three-color LED warning system, light system. We will add the light system also, upgrade the system with wireless communication and cloud storage. Thank you for listening. This is all, and we will come with the final project presentation and final project hardware. We will show the video how the system works, and for further information you can call any of the members and the supervisor.